So I wanted to thank CT, thank you for the introduction, and thanks to IMS for hosting this meeting, and the organizers for all the work that they did to put it together. And thank you all for making, some of you came a long way, so thank you for making the trip. I really appreciate it. I've been in the mathematical logic business now, it seems like, for a very long time. Though I still think of myself as a recent PhD. And through the time, I've learned a lot of math from people, and I've come to admire my colleagues quite a lot. And over the course of things, collaborated with people, talked with people, learned from them. And it's hard to tell after so long in the business. Is the friendship a side effect of the math? Or is the math a side effect of the friendship? And as time went on, it's the second of the two that's been more important to me. So I greatly appreciate your company. Okay, so my talk today is Finding Randomness, which the title is supposed to make you think of something friendly, sort of like Finding Nemo, something like that. So we're going to do a sequence of case studies wherein you find randomness in different forms and try to get a qualitative understanding of how it works. So here's the outline of what I want to do. So this is the first lecture, that's the second lecture. So in the first lecture, it's going to be sort of a reprise of work that I did with Jan Ryman some years ago. So if you're young enough, you may not have seen me talk on this. And if you're old enough, you've probably forgotten what I said. So there'll be something fresh for everybody. So the thing that I want to dwell on is and then, well, let me say what the second talk is, and then I'll tell you what I want to look for in each case. So the second talk is, the first talk has to do with kind of general notions of randomness, and this particular randomness for fairly arbitrary measures. And the second one is looking at the properties of measures and seeing what geometric or analytic properties about measures are reflected by the behavior of the reals which are typical with respect to those measures. So we're going to look at measures with the mass distribution property, which are a sort of central tool inside geometric measure theory. And then we'll look at measures that have well-behaved Fourier transforms. And those and such measures are a central tool in the study of uniform distributions and various aspects of transcendental number theory. And then we'll look at how those aspects of transcendental number theory display or manifest features of randomness and failures of randomness. Okay. So the thing that I wanted to look at in each case is something that's fairly familiar if you've been studying these kinds of things, which is you can think of randomness there are two different aspects of randomness. One is you could sort of think of it like a second order way of understanding it. A real is random if it doesn't belong to it doesn't belong to a small set. It's not exceptional, right? But that is talking about sets, and the real is not an element of that set. So it feels sort of at the level of talking about second order theory of the reals, different sets, and of living in the sets of full measure. The second aspect of randomness is the descriptive property. It's something that you might think is first order over the real. The property that you don't have to refer to the continuum at large, you just refer to the real number itself. Right? So is it approximable? Is it definable? What features does it have internally? Are its digits uniformly distributed? Things like that. Okay. So those two aspects of randomness, right, are pervasive. Whenever you as a logician or recursion theorist study randomness, those are the kinds of comparisons that you make. Compare the point-wise properties of the real versus sort of the global properties of the measure for which the real is supposed to be typical. Okay? So we're going to look at that. In each one of these settings, we're going to look at that duality and see how it plays out. So the first part, I think this part, like I said, will be familiar to a lot of you, but I want to do it anyway. And the second part, there'll be some features which are new to this talk. Okay, so let's get started. So to review, C is Martin-Wolf random if it doesn't belong to any effectively null G delta set. Okay, so this is like I said, it doesn't belong to any it's not exceptional. It doesn't belong to a small set. Okay, so. And then effectively G delta is you have a uniformly RE sequence of open sets of geometrically shrinking measure, and the random real doesn't belong to their intersection. Okay, so this way of looking at things, you could identify any family of sets, any countable family of sets of measure 0, right, and say that a real is random if it doesn't belong to any of them, and almost every real will be random in that sense. Okay, so this way of setting up randomness can be parametrized by the types of null sets that you examine. Okay? And you can turn it recursion theoretic by asking that the sets of full measure that you're talking about, or the null sets you're trying to avoid, are definable. Okay. The other half is randomness as formulated by this kind of point-wise property. So here I call it compressibility. So a real number is algorithmically incompressible if and only if there's a C such that the Kolmogorov complexity of the initial segments of the real are greater than the length of the real minus C. Okay, so you can compress by a few bits, but no more than that. All right. So again, this is something that you could parameterize. This notion of compressibility or approximability is something that you could parameterize by looking at this function k. Right? How are you going to formulate the notion of approximability? Right? You could, like I usually do, go up. You could allow for more and more resources to be available to the compressor, or you could go down. You could make the compression more constrained. It has to be more tangible somehow. Okay. Okay, so the theorem that everybody likes in this area is this theorem of Snore that says that these two properties, when the tool that you're using is the notion of Turing computability, these two aspects of randomness, right, are equivalent. A real is Martin-Wolf random if and only if it's algorithmically incompressible. Okay, now, is this a feature of the theory, or is it a bug in the set of capabilities that we have allowed our null sets and our compressors to enjoy? Okay. So we'll see. Okay. I think that these two aspects of randomness are different. And this particular tool, this particular measure of those two things is not sharp enough to make the distinction. Okay, so we're on the hunt then. How can we find ways to distinguish two things that seem qualitatively different? And maybe they're not. All right, so The rest of today's lecture, I want to talk about work with Jan Reimann. The work is all joint with him. I'm the one who made up these slides. And anything that's wrong about the slides, misstatements, typographical errors, conceptual misunderstandings, I did those independently of the collaboration, and I should get full credit. Usually I don't break collaborations up. You know, it's a joint paper, it's joint, but not in this case. All right, so I'm going to sweep all kinds of details to the side. Right? There are subtle questions that one can ask about representations of measure, and etc. And especially in the realm of computable, when you're looking at Martin-Luff randomness, I'm going to disregard all that. So, but there is a much deeper story than the one I'm telling. Okay, so representation M of a probability measure mu on the Cantor set is a way to provide rational approximations to the measure of each interval. If you think of bracket sigma as the set of reals the set of elements of the Cantor set, so I'll call them reals, the set of reals that extend sigma, you have to say you have to give an approximation to what the measure of each basic open set is, right? And that's enough to represent the measure. If you know the measure of all the basic open sets, you can extend to the measure on the whole space. So that's the representation of the measure. Then I'm going to say that a real x is n random relative to the representation of the measure if and only if it doesn't belong to any, so this is n random, doesn't belong to any recursive in m to the n minus 1 presented G delta set of measure 0. So just lift the resource up. First, you're looking at randomness for some measure, so you get to use the representation of the measure in testing for randomness. And then you can parameterize how random you are by iterates of the Turing jump. Okay. Okay, so now in talking about it, I'm going to stop talking about the presentations and just talk about randomness relative to the measure, but there's always an underlying real number that there's always an underlying description of the measure, and I'm talking about randomness relative to that description. So the first theorem is the following fact. If you don't put any restrictions at all on the probability measure, then x is being random relative to some measure. So x, you could say, has some random content. Right? This turns out to be a trivial notion, right? That the following are equivalent. X is not computable. And secondly, there is a measure such that the measure doesn't concentrate on, I guess there is a really trivial case. Every set is random for the Dirac measure that puts all its mass on the set. If all the mass lives on singleton x, then x doesn't belong to any null set. So if x is an atom of a measure, it's random in the sense of avoiding null sets. Discard that example. Right? After that, if x isn't an atom, right, then it's not a trivial case of x as being random. But if x is not recursive, there is a measure such that it doesn't make x an atom, it doesn't concentrate any mass on x, and x is one random relative to that measure. Okay, so looking for randomness inside x by finding a measure such that x is typical for that measure without being an atom doesn't give you any insight into what randomness is. It's only that recursive sets can't be random. If a set is entirely predictable, right, if it is computable, then it can't be random unless it's an atom. All right. Okay, so this looking at arbitrary measures doesn't really shed much light on what it means to be random. Oops, there we go. So what's the proof? So I'll mention this proof because we're going to see a way to extend the ideas here in a little more sophisticated way. So the way that the proof goes is there's just a couple steps to it. The first is you can apply the Posner-Robinson theorem to find a G such that relative to G, X looks like the Turing jump. Okay. Now, it's known that if you have a real that's Turing equivalent to 0 prime, well, then it's Turing equivalent to a random real, because there is a random real of degrees, Martin-Wolf random real of degree 0 prime. Okay, so relative to this G, X is Turing equivalent. So we're trying to find X looks random relative to some measure. Well, relative to G, X looks Turing equivalent to something that's random. Okay, so that's step one. Okay, so, and that's what this note says. Right? Once you get the jump, you get Turing equivalence to something that's random. Now, a Turing equivalence is a partial continuous map. Right? And it's a map that maps you from 2 to the omega partial to 2 to the omega, right? And it equates X with something that's random. So if you want to get a measure relative to which X is random, what you have to do is complete that partial map, right, into something that's total. And you can use that total map to transform a Lebesgue measure into another measure. X gets transformed, you take Lebesgue measure and you transform it into something else. So the random real for Lebesgue gets mapped to X. X is then random for the transformation of Lebesgue measure. Okay? That's how the argument goes. And how do you take something that's partial and complete it? Well, it's compactness. That's what the compactness theorem says, is that if you have some partial consistency and you want to complete it to a totality, right, then it's possible to do that. That's what compactness says. Okay, and then you have to argue that you can prove a version of the compactness theorem which preserves randomness, preserves the notion of randomness, and that's how the argument goes. Okay, so this previous result was just for one randomness, Martin-Wolf randomness. Okay, so this was specific to everything is being done with one quantifier. If you look at a measure and you look at a few quantifiers of what's definable over the measure, well, if I have a description of a measure and I allow myself a couple jumps, right, then I can pick out what are all the atoms of the measure, right, and the complement of the set of atoms of the measure, right, throw the atoms away, and now you have a measure on what remains. If the measure is completely atomic, in other words, the entire mass lives on atoms, when you throw away the atoms, you don't have anything left. You have a null set. Okay, so if you have a purely atomic measure and you throw away the measure that lives on atoms, and what you're left with is null, everything that is not an atom is not random. Okay, so in a few quantifiers, the atoms don't matter. If I'm looking at measures for which X is not an atom, and I want n randomness, right, you can throw away what's happening on the atoms and look at the measure on what remains, right? And X has to be random in that. Okay, so if you're pumping up if you're looking at randomness with not the computational constraint, but more allowing yourself a larger reservoir of null sets that the typical thing has to omit, you might as well look at continuous measures, because the atoms only obscure things at the low quantifier level. Okay, so that's what we're going to move to now. Randomness relative. When is it that X looks random relative to some continuous measure? Okay, so here are the theorems that I want to mention. So the first is that if you take any n greater than 1, greater than or equal to 1, then for all but countably many x inside the Cantor set, there's a continuous measure mu such that x is n random relative to mu. Okay, so the problem of starting with an x and inverting x to a measure for which x looks typical, right, can be solved. That inverse problem can be solved, except for countably many reals. There's some countable collection of things which just can't look random for a continuous measure, no matter what measure you try to use. They are they're just like several people in this room. They are completely atypical. Actually, and that's good. I prefer to think of myself as atypical. All right, so except for countably many, no matter how you look at it, no matter what features you factor out, et cetera, no matter how you concentrate the measure, right? Those countably many things cannot look typical. They can't look random. But everything else, except for a countable collection, everything else there is a measure relative to which that thing is typical. And then the second part is that there's an interesting aspect to the proof here, namely you can't prove, this statement cannot be proven using only finitely many iterates of the power set of the reals. Okay, now this fact, it's short to state it this way, but what's really underlying that fact is the duality between not being random and being definable. Okay, so it's the things that cannot look random relative to any continuous measure have an intrinsic definability property, right, which is what thwarts the randomness. Okay, so I'll say more about that after we've walk through the proof. Okay, so so we're now going to dive into the proof a little bit. So the first thing to do, if you wanted, we're trying to prove, now talking about this theorem 1, so we have to construct measures. Given an x, except for countably many cases where there's an obstruction, we have to exhibit a measure. Okay, so how do you go from a real to a measure such that that real looks definably random relative to the measure? Okay. Well, obviously you have to use recursion theory. So the first thing to do is to translate the condition, the second order condition that there exists a measure. Right? We want to translate that into some property of x. Right? What is it about x which could guarantee that there is a measure? So we want to localize our discussion to the properties of the real x. Okay, so we're going to translate the condition that there exists this mu to a condition on x as being like we did with the previous argument. We used the Posner-Robinson theorem to transform x into something that was equivalent to a random. Okay, so we want to see what's the condition that we have to realize in order to see that x can be seen as random. Okay, so a little notation. For x and y and z and 2 to the omega, we're going to write x is Turing equivalent to y relative to z to indicate that there are Turing functionals which are recursive in z. And the first one maps x to y and the second maps y to x. Okay, so relative to z, that x and y have the same Turing degree. Okay. When these functionals are total, right, then x and y have the same truth table degree relative to z. Okay. So like I said, Turing reductions correspond to continuous functions that have partial domain, and truth table reductions correspond to continuous functions that are total on the compact set 2 to the omega. So here is the relevant proposition. If you have x and z are elements of the Cantor set, so they are subsets of omega, correspond to subsets of omega. There's a continuous function mu, which is recursive in z, and x is n random relative to mu and z. Okay, so you get to throw z into the description of the Martin-Luft test, and you also get the description of mu in there. Okay, that's equivalent to saying there's a continuous dyadic measure, which is recursive in z, and x is n random to that measure. So you can take if you have a continuous measure, you can transform the measure, you can tweak it here and there so as to make a better measure, one so that every interval has dyadic rational measure exactly. Okay? So that removes some of the ambiguity of how the measure is presented. And then the third case is that there is an R such that R is n random relative to Z, and there's an order-preserving homeomorphism from 2 to the omega to 2 to the omega, preserving lexicographic, the usual order on 2 to the omega, such that f is recursive in Z and f of R equals x. So in other words, you have a continuous order-preserving map. So you could push forward Lebesgue measure under that map. The measure of an interval in the image is the Lebesgue measure of its pre-image. So it's like taking a rubber band and you squeeze it here and it gets thinner there, and you're just stretching and compressing the measure. So you can think of it as, I don't know, think of it as exactly that. Right? That's this continuous homeomorphism is sometimes big intervals go to small ones, and sometimes small intervals pull back to sometimes big intervals pull back to small intervals. But it's a rearrangement of mass along the unit interval. Okay, and then the last example is that there is an R such that x is n random relative to Z and x. And x is TT equivalent over Z to R. Okay, so there is a continuous measure if and only if there is a truth table reduction which would transform the randomness of R for Lebesgue into the randomness of x for the induced measure under the map. Okay, so Laurent has written papers like this. There's only one randomness in this context, right? It's transformation of Lebesgue measure randomness under, in this case, continuous, such a continuous function. So if you're looking for randomness, you want to look for, if you're looking for a way by which x looks random, you want to look at a way to transform randomness in the usual sense, right, to x, so that the transformation, right, gives you a measure that makes x look typical. Okay, so that's the goal then. How then can you take an arbitrary x, right, except for countably many exceptions, right, and get x to be equivalent, right, to a random real relative to some z? Okay, so in order to conclude, so I said how can you do it, but this is what we have to do. If we want to conclude that x is n random relative to some continuous measure, we should find a z relative to which x is truth table equivalent to some n random sequence R. Okay, so previously, that's what we did. In the previous argument, right, the argument for arbitrary measures, that's what we did. We used the Posner-Robinson theorem to get x equivalent to the Turing jump of G, but then the Turing jump of G is something that's random relative to G. So relative to G, we got x to be equivalent to something that was random. And then we proceeded to use that fact. That was a Turing equivalence. It wasn't a truth table equivalence. Okay, so, but nevertheless, let's start. So we can start to fill in our picture here. If we want to get x as n random relative to some continuous measure, it's sufficient to find a z relative to which x is truth table equivalent to an n random sequence R. Okay, so when can we immediately say that's impossible? Well, if x is recursive, right, x is not equivalent to something that's not recursive relative to any z. So if x is recursive, x cannot satisfy this condition. So recursive sets cannot look random relative to any continuous measure. So if here is, over the years I've learned quite a lot about the structure of the Turing degrees, and I've concluded that they look exactly like that. So that's I think an accurate graphical representation of the Turing degrees. And if you're not that experienced in the study of the Turing degrees, that north getting to be more complicated. And this little point here is the Turing degree of the recursive sets. And the recursive sets are not relatively random. Okay, so we're rapidly filling in our picture. We need, let's go to the phase 2, right, of our analysis. And that's going to be an invocation. This is recursion theory and higher recursion theory and set theory. So we're going to use a little bit of set theory. One way, right, to show that there exists interesting real numbers is to invoke Martin's theorem. So this is Martin's theorem for Borel, and it's really for Borel Turing determinacy. Okay, so suppose that you have a Borel subset of 2 to the omega, and for every real number A, there is a y such that y can compute A, and y is a member of that Borel set. Okay, so cofinally in the Turing degrees, you have representatives of the Borel set. Okay? Then there is a B, so there's a single real. This is the interesting real. There is a B such that for every x greater than or equal to B, there is a y that's Turing equivalent to x, and y is in B. Okay, so if you look at the degrees that are represented by elements of the Borel set, there is a B such that everything that's above B, right, is such a degree. Okay, so if you have a cofinal set of Turing degrees, it contains a cone. That's the usual way of saying it. A cofinal Borel set of Turing degrees contains a cone. Okay, so we're going to use that. We're going to use that fact to construct measures. Okay. So here's the corollary. For any n greater than or equal to 1, there is a B such that for every x Turing above B, there is a continuous measure such that x is n random relative to that measure. So we're going to go from Borel determinacy to the existence of measures. So what's the proof? Well, the first thing to note is that if x is Turing equivalent, this is a fact about random reals, if x is Turing equivalent to an n plus 1 random relative to z, then x is truth table equivalent to an n random relative to z jump. Okay, so random reals are GL1. Right, so you can reduce Turing equivalence to TT equivalence if you take a larger base. All right. Secondly, that's the first fact. We can go from Turing equivalence to TT equivalence. And since we're looking relative to some side parameter, it doesn't matter if we look relative to z or z jump. They're just something relative to which x looks random. Okay, now this tells us if we know something about Turing degrees, we get something about truth table degrees. The second observation is you can consider the Borel set of y's such that y is Turing equivalent, or you could say even is of the form, the join of A plus R, where R is n plus 1 random relative to A. Okay, so I am the join of something which is recursive in me and something that's random relative to it. If it's n random, that's an arithmetically definable set. And for every A, there exists something that's of the form A plus R. So that set is cofinal in the Turing degrees. Okay, so that means that there's a cone. There's a cone of reals in the Turing degrees such that every element, every point in that cone, there is a B, so that everything that can compute B is Turing equivalent to something plus a random. Fantastic, right? So inside that cone, any degree is Turing equivalent to something plus a random, but then it's TT equivalent to that random over the jump of the thing. And consequently, there exists a measure that makes it look random itself. And that's this corollary. So it's an interesting way to come up with a measure. And you prove that there exists a measure by invoking this feature. Okay, so that lets us fill in the picture a bit further. which is that there's a cone. There's a cone of reals. This point is B, the base of the cone you get from Martin's theorem. There's a cone of reals such that every real in that cone is relatively random relative to some continuous measure. Okay, so there's a lot of stuff, right? There's a lot of stuff that if you take any cone, right, there's a lot of things that don't belong to that cone, right? Typically, a set of measure 1 is not, that's the Sachs's theorem, that the set of things that are above the base of this cone is a null set. Okay, so we have a little way to go, but in order to convert this picture into something where all but countably much is blue, all but countably much is relatively random. Okay, so now that's the plan. All right, so Martin's proof, the proof of Martin's theorem that shows that if G, the proof it's a proof in set theory, right? And the amount of set theory that you need to run the proof is something that you can quantify. Okay, so Martin's proof implies that if G is a real parameter used to define the Borel set B, then the base of the cone of things that belong to that Borel set, this is Roman B, belongs to the smallest countable model of a sufficiently large subset of Z of C, the axioms of set theory, to which G belongs. So now we're thinking about definability. We have a real number G. It defines a Borel set. Right? That set is cofinal in the Turing degrees, so that Borel set contains a cone in the Turing degrees. Okay. What is the base of that cone? Where does that blue wedge, what's it resting on? Okay. Go to the proof of the theorem that shows that the base of that cone exists. Right? You can run that proof. That's a proof in set theory. Right? So you can see what axioms you need. Right? Okay, then you can look at the smallest model of that set of axioms. It's going to be some little initial segment of Gödel's constructible universe. Right? So you can run that proof inside a little countable model. Right? Now, and then you prove an absoluteness theorem that if the model thinks that B is the base of the cone, then B really is the base of the cone. So that's this. The B, the place where the eventual behavior occurs in the Turing degrees, you can figure out where it is. Okay, and it belongs to the smallest countable model. That's some little initial segment of L. Okay, so let's let L lambda n be the smallest countable model satisfying the axioms of set theory without the power set axiom. And so you get the usual axioms of set theory without power, and then add n many iterates of the power set of the reals. Okay, so that's some fragment of ZFC. In ZFC, you can prove it's consistent, and then there's an initial segment of L in which it's true. And by Lowenheim-Skolem, that's countable. All right, now. So here's the theorem. Suppose X is not an element of that countable model. Right? Then there is a G such that L lambda n of G is a model of Z of C minus, and the same theory, there exists n many iterates of the power set. So G preserves the closure of L lambda. Right? And secondly, every real number that is inside this model, L lambda n of G, right, is recursive in G plus X. X is the thing, so this is an amped up version of the Posner-Robinson theorem. Right? X, in the Posner-Robinson theorem, you took something that wasn't recursive, and relative to G, it looked like the jump. And here we take something that's not in L lambda n, right? And we find a G so that relative to G, X looks like it knows everything about L lambda n. It looks basically universal for L lambda n of G. Okay, so if it's not recursive, relative to some g, it looks like g jump. If it's not in L lambda n, relative to some g, it looks universal for L lambda n of g. Right, so it's a generalization of the Posner-Robinson phenomenon. Okay, so the proof uses a forcing that Masahiro Kumabe and I introduced, and you use this forcing, which we first thought of it in looking at the Turing jump and finite iterates of the Turing jump, but it applies perfectly well inside this structure. And secondly, there is a corollary, right? Which is if x is not inside L lambda n, then relative to g, right? X knows all the reals that live inside L lambda n of g. In particular, x and g. So relative to g, x knows the base of the cone above which everything is relatively random. Okay, so relative to g, x is in the cone of relatively random reals. So relative to g, it looks like it's random relative to something. So relative to g and that something, it's random, which is what we wanted to show. Okay, so that's the theorem. For any x which is not in L lambda n, there's a continuous measure mu such that x is n random relative to mu. Okay, so what's the countable set of things? What's the countable set of things that don't necessarily look random? Well, the reals that are inside L lambda n. Okay, so it's a little countable set that includes every real number you've ever heard of, unless you are Feng Qi. But unless you've heard of zero sharp or things like that, this includes every real number that you've ever run across. So except for all the real numbers that you've ever seen, right, everything is relatively n-random. Okay, so that's a fairly large envelope to put around the things that can't look random. Okay, but nevertheless, it is a countable envelope. So for all but countably many x and 2 to the omega, there's a continuous measure, such that x is n random relative to that measure. Okay, so that lets us extend our picture to there. And depending on your point of view, it depends on your sort of, I guess, professional experience. You could think of this blank area, the area on which we don't have any information yet about being random or being relatively random or not. You could think of that blank area as either really small because it's some countable little initial segment of L. It doesn't include basically anything. Or you could think of it as really huge because it's way beyond the arithmetic sets or the hype sets or the et cetera, et cetera. I tried to compromise and make it look, medium. Right? So everybody can think, well, this is huge, or you can think, oh, that's pretty big. Let's all be friends. Okay, so what about the inner structure of this blank bubble? Okay, so we have that empty bubble, and we'd like to find out what is in there. What is it that is driving the impossibility of looking random? What's the so now I want to get to this duality between looking random and being indescribable or non-approximable or et cetera, et cetera. Okay, so what is it that's, whoa, what happened there? I was in the right spot. What is it that is imposing its will on the real that makes it look not random from any perspective whatsoever? Okay, so what we're going to do is walk through the analysis to try to figure out what is, if we go back to this thing, what's what's keeping that from collapsing? What are the real numbers inside there that are making that white part, what's a lower bound on how big that white part is going to be? Okay. And once we see what those lower bounds are, then that will, as a corollary, give us the meta-mathematical fact that you can't prove the theorem that I stated about co-countability using only finitely many iterates of the power set. But that's sort of a very far downstream, and in some ways the least interesting aspect of things. The interesting part is what is it that makes things fail to look random from any point of view? Okay, it's a corollary of what we actually describe that gives us this fact that in some sense the use of Borel determinacy could not be removed. You need like Borel determinacy, you need iterates of the power set to prove the theorem. So I should give credit to Harvey Friedman, who proved that about Borel determinacy, and it's true of this consequence of determinacy as well. Okay, so I need to know a couple things about randomness, and then we will get the argument to work. So suppose that you have some natural number n, it's bigger than or equal to 2. Y is some real, and x is random relative to mu. Okay, so if I is less than n, so n is the degree of randomness that x holds relative to mu. If I is less than n, so below the randomness, x looks random up through and past I. Okay, and y is recursive in x plus mu. Okay, so if using the random real and the measure, you can compute y, and y is arithmetic in mu. Okay, so y has a light face definition relative to mu. So y is definable from mu, right? Using a few quantifiers, and it's computable from mu using the random real. Then y has to be recursive in mu. So randomness doesn't speed up it doesn't make definable things more easily defined. Right? So random real, this is another reflection of for every non-recursive set, the set of things that compute it is a null set. And this is just quantified a bit. Okay, so if you can compute from a random something that's definable, then you could actually have computed that definable thing without the random. Okay, so here it is with less information. Using arithmetic definitions with fewer than n quantifiers, n random reals don't accelerate arithmetic definability. So that's the thing to keep. That's one feature of randomness to keep in mind. It doesn't let you give better computations of things that you could already define. Okay, so that fact, right, leads to the following argument. Right? For every k, 0 to the k is not too random relative to any measure mu. Okay, so 0 to the k can be quite complicated. Right? It's, you can't define it in less than k quantifiers, but it can't look even too random, no matter what measure you use, provided the measure is continuous. So what's the proof? You know what to do when you want to prove something. The first thing you do is decide, I'm going to prove it by contradiction, because that gives me more to work with. So, never fails to do that. Okay, so secondly, so assume that it's too random relative to mu. So it's 0 to the k. Well, then 0 prime is recursively enumerable relative to mu, because it's recursively enumerable relative to everything. Right? And it's recursive in 0 to the k. Right? So now I have something that's too random. It can compute something that is sigma 0, 1 definable. Right? It better be the case that the measure computes it, because the too random can't accelerate right? The computability of definable things. Okay, so that means that 0 prime must be recursive in U, which means that 0 double prime is RE in U. And then you can use induction. You can just eat up all the iterates of the jump from below until you get to K by iterating the fact that the random real can't accelerate the computation of a recursively enumerable set. So even though these are quite complicated reals, recursion theoretically speaking, they can't look too random. They have an internal self-generating structure, right, which random reals cannot exhibit. Okay, use induction. So you proofs by contradiction and you use induction. And if you can do that, you can solve 90% of the problems in mathematical logic. And just remember those two things. And the other 10%, you have to use compactness. And then you're all, I shouldn't have told you all that. That's been the secret to my success. Yeah, Gerald Sachs once told me, or he told Andrea Sorby about me, that the secret of Ted Slaman's success was fast typing. But really, it's use contradiction. All right. Okay, so there's the second feature that we need to know about this. What can you compute? What can you compute from a random, or what can you fail to do with a random? Is the following: not only can a random not accelerate the computation or the arithmetic definability of arithmetic sets relative to the random, you don't get a better arithmetic definition. The same thing is true about well-foundedness. So linear order is well-founded if and only if every non-empty subset has a least element. And if you have sufficient randomness, if n is greater than or equal to 5, then n random reals cannot accelerate the calculation of well-foundedness. So if using a sufficiently random real, you can compute the well-founded part of a recursive linear order, then you could have computed it earlier. You don't need the random. You could figure it out without using the random. Okay, so those are the two facts. So the two facts are that random reals don't let you accelerate arithmetic definitions, and they don't let you accelerate the calculation of well-foundedness. Okay, so now we want to run that argument that we did for the Turing jump, except we want to extend it as far as we can. Okay? So the natural extension of the jump hierarchy, right? The first one is you go through the hyperarithmetic sets, but then the jump hierarchy extends even further. Right? If you go through limits, well into the world of the constructible sets. Okay, so the Gödel's hierarchy of constructible sets is defined by the following recursion. I'm putting it up because I want to make a comment about it. You start with the empty set. At step alpha plus 1, you look at all the collection of things that are definable with parameters from L alpha, definable over L alpha. And at limits, you take unions. Okay? So there's two things that are happening there. This, if you break down L alpha plus 1 from L alpha, it's the iteration of the Turing jump. Each step along the way, it's the existential quantifier, right? And the existential quantifier, it's things that are defined in a sigma 1 way, things that are defined in a sigma 2 way, which by Post's theorem is sigma 1 over the things that you'd already defined in a sigma 1 way, etc. So the iteration of L is quite similar to the iteration of the Turing jump. Except for the Turing jump, we're talking about real numbers, right? And the existential number quantifier, and here we're talking about sets. Okay, so I'm going to look at the case where we're looking at initial segments of L in which every set is countable. Okay? You never have something that looks like omega 1. Right? It's L lambda is the smallest well-founded model of ZFC minus no iterates of the power set of omega. When you have to do the proof here with finitely many iterates of the power set, it gets a little technical, but this is what you try to do. Okay, so we said, as you go up through L lambda, each L beta is a countable structure obtained by iterating first-order definability. Right? And as you work through L lambda, because you never construct a set which even temporarily looks uncountable. Every time you do this step in Gödel's hierarchy, not only do you construct the new set, you construct a counting of it. Okay? So now we're in the realm of computable structure theory. We have codes. We have these initial segments of L, but we also have the codes, the real numbers which code them as countable structures. Okay, those are called Jensen's master codes, and they're the natural iteration, the natural extension of the iteration of the Turing jump through the transfinite. Okay? And they are constructed in two ways. The first way is you take the master code and you take its Turing jump, basically. You look at what's existentially definable over the structure that's coded by the master code. Good. So that's the kind of thing that we've already discussed. You can't accelerate taking the Turing jump. And secondly, you can take direct limits. Okay? Now, there's a nice recursion theoretic fact. If x is above all the arithmetic sets, then x double jump is above 0 to the omega. So recursion theoretically, you can't, in a couple jumps, if I know all the arithmetic sets, in a couple jumps, I know the natural direct limit, right? 0 to the omega. But we're looking at randomness with several quantifiers. Two quantifiers can't accelerate the definability of things. So the two operations of taking the Turing jump and taking direct limits are things that we can talk about in the codes, and that they fit in with the analysis that we've already been doing. Okay, so what happens? You've got this initial segment of L. It has a parallel structure internally definable of all the master codes that describe the countings of all of its initial segments. And every real inside that initial segment of L is recursive in one of the master codes. Okay. Okay, so then there's the theorem that says there is an n such that for all beta, a limit ordinal, if beta is less than lambda, then there's no continuous measure such that m beta is n random relative to mu. So the master codes have the feature that the iterates of the Turing jump had. They can't look random. And the proof is similar to the proof I gave for the iterates of the jump. You suppose that it's random. Inside M beta, you can look at everything that you can compute that looks like a master code. Right? You can read off from that the well-founded part. Right? M beta can read it. Well, all right. Perhaps because of the issues of time, I won't get too far into it. Let me just say that you use a generalization of the jump argument to give a contradiction. The master code has built into it a self-generating description, how to build it up in steps where each step is either take a Turing jump or take a direct limit of what you've got so far, which you can do in two jumps of what you had so far. And the master code is computing all those things. They must all be computable in the measure. Contradiction. The master code itself has to be computable in the measure. Okay. So it's a generalization of the jump argument. Okay. So L lambda doesn't satisfy the co-countability theorem, so ZFC doesn't prove the co-countability theorem. L lambda doesn't satisfy it because these master codes are co-final in the reals that belong to L lambda. Okay, so here's the picture, filled in a little bit more. Right? Sitting inside this bubble is the jump hierarchy. Right? It's extended into the transfinite. Right? And it's co-final. So the spine on which non-randomness lives is the hierarchy of the Jensen master codes, which are explicit definable sets that have an internal way to definably generate themselves by simple steps, where the steps are take the Turing jump or take a direct limit. So these aren't the only things that are impossible to look random, but they generate them all. Okay, so manifesto. Structure is the antithesis of randomness. Right? So if something is definable, if it's well approximable, if it has some kind of identifiable, definable pattern, that's what stops it from being random or looking random. And in this case, it was the universal sets for the iteration of the existential number quantifier, namely the master codes, were exactly what was the feature of denying randomness. Randomness from any, you can't sort of average out the behavior of these sets so as to look at a whole class of sets that have the features that these sets have. And so these sets would be typical. There is no measure that takes the behavior of these sets and sort of spreads it out onto a lot of reals that look like that, and this guy is typical. That doesn't happen. Not for those things that have this internal self-generating structure. Okay, so then let me end with some questions. Sorry, I'm a couple minutes over. Question 1. As a set of reals, is the set of things that are never continuously random an arithmetic set? Is it a hyperarithmetic set? Is it pi11 complete? It's a countable set, but I'm asking for its light-face complexity. Right? If you have the real that just enumerates its elements, sure, it's a trivial set. If you don't, how hard is it to define it? Right? The best that we've been able to say is it's pi11. Okay, if it is pi11, well, it is a pi11 set, does it have a natural norm? Is there a way to stratify that set? And I believe if it has a nice natural pi11 norm, right, and it goes through the recursive ordinals, we're going to get some interesting detailed information about the structure of that set. Okay. You have to look beyond the delta 2 sets, though, if you want to see complexity, because on the delta 2 sets, it's arithmetic. This is a more technical problem. Is the set of reals that it cannot look too random relative to any continuous measure contained in the hyperarithmetic sets? Set of reals that can't look one random is contained in the hype sets, but the two randoms, I don't know. There seems to be a big jump between 1 and 2. Like it doubles. Okay. Question 3. This one was asked of me by John Steele. So this is really a set theorist's take on it. Right? You have a theorem that you can't prove in a certain fragment of set theory. The natural reason why you can't prove it is that it proves the consistency of that fragment of set theory. That's the consistency strengths are always supposed to be linearly ordered. This one, can't be proven down low, so it probably has consistency strength that's too high. But I don't know the proof. I don't know. This probably is the most accessible of the questions I'm asking, but I don't know how to do it. So I'd like to see the answer to that. Then that would be an improvement of the theorem. It'd be a much sharper theorem than the non-provability. And then last is a question due to Andrew Marks and Adam Day, though I changed their notation slightly. So say that a measure is awesome. If it's the push forward, like I said, you have a continuous map, and the measure of this interval is the Lebesgue measure of the pre-image. So it's a push forward of Lebesgue measure by a continuous degree invariant injection from 2 to the omega to 2 to the omega. Say that x and y are n related if they're both n random relative to the same awesome measure. And take the transitive closure of that relation. So the question is there an x that is equivalent to something that has Turing degree x jump? So can you find these degree invariant measures such that x and x jump, right, both look random in a kind of related way. And secondly, does that equivalence relation contain a cone? And that's it for today. Thanks.
Any questions? Comments?
Hold your questions. Oh, sorry. No, go ahead, Steve. I wasn't expecting a question, but go ahead. Yeah, if n is greater than or equal to 5, then and n so you have a linear order, and relative to this high degree random, right? You can give a simple definition of the well-founded part of that linear order. Right? Then you can give a similarly simple definition without using the random of the well-founded part of that order. Okay, so that's the proof. That 5 comes out of the proof. So like the proof is it's not a perfectly straightforward fact. So the proof needs to analyze some. You have to set up the right structure to analyze it. Adam? Yeah. So you can look at it's the strategy of the game where the payoff set is you produce a real of the appropriate type. Right? Now, the way that the arguments work is in the proof of Borel determinacy. There's an initial you can prove Borel determinacy up through the first 4 levels of the Borel hierarchy without iterating the power set. But after that, every new quantifier adds a new iterate of the power set in order to prove the determinacy theorem. So if you want to prove the determinacy of some game that has a sigma n definition, n iterates of the power set will do the trick. And you could sharpen it, n minus 4 or so. So then you just look at what does it mean to say that you can compute a measure relative to which you are equivalent to the measure plus a random. That's a Borel set. It's the thing that you can compute, and you're looking at n random. So you compute some things that have an arithmetic property. Right? So the measure plus r is Turing equivalent to u, and r is n random over the measure. Okay, so that n, right? That n is going to tell you what's the complexity of the payoff set. Right? And the strategy for a payoff set of that complexity is the base of the cone. Right? And in order to get that strategy, you need to look at a model of ZFC plus that many iterates of the power set. And then Martin's theorem is true in that model, and the thing that the model thinks is a strategy or is the base of a cone actually is the base of a cone by an absoluteness argument. So you just count the quantifiers, and that's the number of power sets. That's an upper bound on the number of power sets you need. Oh, thanks. Yeah, oldies but goodies. It's like I was thinking about what would it be like for me to hear a talk on something that I heard a long time ago, and I thought the closest analogy is watching a movie. I hope it's one of your favorite movies. Watching a movie that I really like and waiting for Lauren Bacall to say, "You do know how to whistle, don't you?" Or Humphrey Bogart, say something like, "Yes, she tried to sit on my lap while I was standing up." So it's. I like this material very much, so it's nice to go back and look at it again. And there are interesting questions. This question number 4 of Andrews and Adams has nice consequences for the theory of Borel equivalence relations. So if you can pick up this material and go at number 4, I think you would really contribute to that theory. Okay, everybody, I'll see you next Monday.